So in today's lecture of Lie algebra, I will be doing this lemma, one of the lemma 4.4, okay, one of the exercise problem it is. Let L be a Lie algebra. If L is solvable, then every subalgebra and every homomorphic image of L are solvable. And the second one is, suppose that L has an ideal I such that I and L by I are solvable, then L is solvable. C part is what? If I and J are solvable, then I plus J is a solvable. Okay. Now this I will be proving it in today's video okay. First question, okay, that A part, this is a lemma 4.4, right? That L be a Lie algebra. If L is solvable, then every M is a subset or contained in L, and every homomorphic image of L are solvable. Or this can be asked in this form. That L be a Lie algebra. If L is solvable, then every subalgebra and every homomorphic image of L are solvable. Okay, let me start with the solution. So if L1 is a subset of L is a subalgebra, and if L is solvable, then L1 is also solvable. So what I'm saying is, if suppose L is solvable, then L1 is also solvable, okay? Because L1 is a subset of L. And okay, so given phi L tending to L1, we want to show that phi of L is solvable. Now what we want to show is that phi of L is solvable, okay? That is, phi of L raised to power of m is equal to 0 for some m belongs to natural. That is the definition from that solvable Lie algebra. Okay, so for some m belongs to natural, given L is solvable, that exists k belongs to n such that L raised to power of k is equal to 0. So phi of L raised to power of k is equal to what? Phi of L raised to power of k. Now this is equal to phi of 0 because L raised to power of k is 0 over here, which is nothing but equal to 0. So this is first part which we have done, and suppose phi of L dash is given to you, and this is equal to phi of Lie bracket of L comma L inside, okay, this entire. Now this is written as phi of L comma phi of L, which is nothing but phi of L of dash, okay, outside. So let me prove the second one, B part of it. Suppose that L has an ideal I such that I and L by I are solvable, then L is solvable, okay? Now what is given? Now given I is an ideal of L, I comma L by I is solvable. To show that L is solvable, now what we need to show here? See, suppose that L has an ideal I such that I and J are solvable. Then we need to show that L is solvable over here, okay? So that's what I have to show. So let me turn the page. Since L by I is solvable, there exists M belongs to natural such that L by I raised to power of M is equal to L raised to power of M plus I upon I, which is equal to nothing but I. See, here it is already given that L by I are solvable, okay? So next thing is what? Since I is solvable. Now since I is solvable, what will happen? Now I is also solvable, right? Here. So there exists k belongs to natural such that I raised to power of k is equal to 0. Now next page. L raised to power of m is a subset of I, which implies that L raised to power of m raised to power of k is a subset of I raised to power of k. Now this will imply your what? L raised to power of m plus k is a subset of 0, this. Because here what is my I raised to power of k is equal to 0. So that's what I have put here, 0. And this is written in this form, L raised to power of m plus k. And this is nothing but equal to 0. So L raised to power of m plus k is equal to 0. Now we will be doing, so we proved the second part also, and now we are going to prove the C part, that is this one. So C part is what? If I and J are solvable, then I have to show that I plus J is solvable, okay? So given I and j are solvable. Now what is given? That I and j are solvable. This is already given. Okay. Now this implies that I plus j is solvable. Therefore, by second isomorphism theorem, which I have already given to you all, this you all can check in the previous lectures. And next, let me turn the page. So by the second isomorphism theorem, what happens? From that note which I have given to you all, I plus j upon I is isomorphic to j upon I intersection j. Next, I'll have to consider that phi times from j tending to j upon I intersection j. Now phi of x is equal to what? Is equal to x plus I intersection j. And then you can say that phi is onto, and by a what happens? By a meaning what it is? By the first one which I have given to you all, by this. By this a. No, this is the a part, this, and this is the b part, okay, this. So directly I will be doing this now. So by second isomorphism theorem, what did I say? This is isomorphic to this. Next I have to consider this, and this part was also done. So phi is onto, and by a j upon I intersection j is solvable. Since j is solvable, I plus j upon I is solvable. Next is what? Since I is solvable, from b, what it implies that I plus j is solvable. With this I am done with the third also, C part also. And in this lecture I will be doing largest solvable ideal of L and semi-simple, the definition of semi-simple, the definition of simple, and along with the remark, and along with the two exercise problems. And if you all have not understanding of the concept, or in this you all have not understand theorem how to do it, refer to the previous lectures and try to get it, or else comment below, I can do it again for you all. Thanks for watching.